Hi everybody, I'm Steve, and this is Rust's journey to Async-Await. There's sort of been this theme. I've given a lot of talks about Rust at QCon, and it seems like I'm always talking about something that's happening like 3 months in the future. So this sort of continues on that trend of things. As mentioned, this is about how we arrived at Async-Await and like the final couple little steps that are happening as well. I'm giving this talk because I'm on the Rust team in general. I'm on the Rust core team and in charge of the documentation team. I work at Cloudflare, although not on Rust stuff. Doing 2 workshops tomorrow, one on Rust and helping out with one on Cloudflare Workers, so I don't know if I'll see any of you there. While I am on the Rust team, I want to emphasize that I was not like directly involved in all of this work. I am primarily doing this as a reporting capacity. I like to think of myself as like an amateur historian of Rust development. I like to keep track of how the language has evolved over time and sort of like deal with these major topics. So I was not directly involved in the design. I just read all the comments and talked to people over years. So I'm kind of giving you my like semi-outside perspective on how this went down. Most specifically, a lot of people were involved in making Async-Await and Rust happen, but a special shout out is deserved from Without Boats, who is the person who has been primarily driving the design over the last couple years. So, Boats is awesome and wonderful. Okay, to start off, to figure out how we actually get to Async-Await in Rust, we sort of have to talk about like what asynchronous programming actually is. And so it turns out that this is really hard to talk about because there are so many different options in the space of trying to make a computer do more than one thing at once. And so the start of this talk is going to involve a lot of definitions, just to make sure we're all on the same page. So, we're going to start off with there. So people talk about asynchronous computing sort of along with these other 2 things, which is parallel computing and concurrent computing. So people get these 3 definitions mixed up all the time, but just to be clear, parallel computing is when you're able to do multiple things at once. Concurrent programming is when you're able to do multiple things, but not at once. And asynchronous programming is actually unrelated to those 2 things. It's a totally different axis. So let's get into this a little bit more. But briefly, there's also this other term called a task. And so this is sort of a generic term for some sort of computation running inside of a parallel or concurrent system. So this may mean a thread, this may not mean a thread, this can mean sort of anything. It's kind of just a generic catch-all term for I'm doing some sort of thing inside of an asynchronous or parallel or concurrent system. So you hear me say task a bunch. It's a very generic sort of word. Okay, so parallel computing. Technically, things can only be parallel if you have multiple CPU cores or multiple CPUs. I chose a lightning bolt for a computational task just because, I don't know, it seemed cool. But we sort of have this like timeline of execution, and so you have these 2 things and they're truly executing independently. This is why this is only possible with multiple cores or multiple CPUs, because you fundamentally can't make one processor do 2 things at once because of physics. Like, it's physically doing a thing. But if you have multiple of them, then they can be doing 2 independent things in one system. So you get parallelism this way. The second one is concurrent programming. And concurrency means that you like pretend that you have multiple cores, but you don't actually have multiple cores. So you do a little bit of work on one thing, and a little bit of work on another thing, and another little work on another thing. And so these 2 things, like all of these options can also be combined. So for example, in a lot of systems, you have different parallel tasks that are executing concurrent things inside of the 2 of them. So there's like all sorts of ways you can fit these sort of things together. And so when we talk about asynchronous programming, we're talking about language features that sort of let you write code that is able to be executed in a parallel or concurrent way. And that's sort of because you need the ability to say like doing things simultaneously. If you think about the way that code normally executes, you have like the first thing and the second thing and the third thing, and they follow down in lines in most forms of programming, not all. And so like you need some sort of way to be like actually execute these things at the same time. And so that's asynchronous APIs. Okay, I'm almost done with terms, I swear. And then we can actually productively talk about this. Cooperative and preemptive multitasking. So cooperative multitasking is when all of your tasks have to cooperate to operate synchronously. Asynchronously. So each task sort of decides when it is willing to give up the particular resource and have another task execute instead. This is the way that I originally learned about this because I think it was Windows 95 came out and had preemptive multitasking, or Mac OS 8 instead of 7 or whatever. And preemptive multitasking, the system decides when you yield to other tasks. So this means that any computation can be interrupted in the middle and handed off to something else. This is a very interesting trade-off because in a system with cooperative multitasking, if you have a bad actor, they can really mess everything up. Because what happens if they never decide to give up control of the situation? Then they just hog all the resources. So in an untrusted system, you often want preemptive multitasking. But being able to do that also adds some overhead and some complexity and some other things. And so if you have a system where you know that you have only good actors, then cooperative multitasking can be a little bit better. It just really depends. But these two things are sort of at odds. And then finally, I think in my big terminology block, native versus green threading. This one gets even more complicated. I'm not going into all the differences here. You also hear things like coroutines and stackless versus stackful coroutines and all these other things. But at its core, there's this sort of dichotomy between native threads, which are sometimes called one-to-one threading. And these are tasks that your operating system provides as an API. So if you're running sort of a process, you're able to say within that process, I would like to execute some tasks. And so it's called one-to-one threading because you get one task for one operating system task, which sort of implies green threads, which comes next, also called N-to-M or M-to-N threading. I don't see it consistently used. Sometimes people put the N first and sometimes the M first. I don't know. But these are when your programming language or its runtime provides you with a task abstraction, and it maps a certain number of its own tasks onto the operating system's threads. So you get N program threads to M system threads. So that's why it's N-to-M and why the other one is one-to-one, because there's a correspondence. A lot of different programming languages are using green threads and have for a long time. Both of these things are interesting, and this particular set of things really gets to the core of why Rust made the decisions that it made in order to do async, specifically around I/O. So there's some advantages and disadvantages to both of them. Everything's a trade-off. There's no free lunch. Native threads have the advantage that they're a part of your system, and so the operating system is able to handle its scheduling. And that means that it can see every task that's executing on the system and make the appropriate choices to do the scheduling because it has total visibility into everything that's running. They're also very straightforward and well understood. Threads are an old technology. They've been used for a long time. They're hard to use sometimes, but in terms of an API, they're not that complicated, and they're super well understood because they've existed for a long time. However, they also have some disadvantages, and these are also system independent. So if you look at Windows versus Linux, for example, you'll get some small differences here, but I'm not going to go super deep into those details. But the defaults around native threads can be kind of heavy, and there's a relatively limited number that you can create due to those sizes. So your operating system needs to keep track of all these different threads, and so it has its own structures that it uses for bookkeeping. And they also have the primary resource that people are concerned with threads is the stack size, so sort of the amount of memory each thread can take. And by default, that's relatively large on Linux and Windows. And so keeping track of that overhead, every time you create a thread, has some overhead, so you can only create so many of them. And given they only have so much memory and you only have so much memory, you can only create so many of them. Green threads, on the other hand, their advantage is that they're not part of the overall system, which is kind of hilarious given that that's also being part of the system is an advantage. It's also a disadvantage. Since your runtime handles scheduling, it can know and sort of prioritize the details about your program and how the bits of your program operate. But the weird downside of that is now you've obscured this aspect from the overall system, so you might get into a battle between your operating system's scheduler and then your program scheduler, and so that can get weird and complicated. But the major advantage that most people talk about is that they're significantly lighter weight. So usually green threads start off with a stack size that's 1/10 to 100th of the size of a native thread, which means you can create 10s to 100s more of them. It's not uncommon in systems that are built around green threads to start up, say, 1,000,000 threads. That's totally reasonable. But it's not something you would want to do with an operating system thread because you would run on RAM. And so there's some disadvantages there, largely around the fact that these are not part of the native system anymore. And so if your green thread runs out of that very small amount of stack, then it has to do something. There are many different ways to handle this, and this is largely where all the different implementations of green threads kind of break down, but it needs to grow and change the size of that stack and then copy the old stack over and do all this stuff. And so that can cause some issues. And then also, when you call into C code, C expects like a real actual stack. And so this can introduce some overhead when you have to switch between the stack from your green thread and the stack from the native thing. And so that can be like a problem. So which one of these is appropriate depends entirely on what you're trying to do. And largely the story that I'm going to be telling you today is about how Rust thought that one of these things was the right way to do things, and then painfully over years slowly switched to the other one, sort of. Okay, so why do we care about any of this stuff at all? This is the end of my giant definitions block. Sorry, there's just so many things here that you have to like piece together to really like form a coherent story about this. I needed to like start off by doing that. There's this old thing called the C10K problem, and I took this screenshot. This was the website that first introduced me to this problem. It's a little old, if you can't tell. It's time for web servers to handle 10,000 clients simultaneously, don't you think? After all, the web is a big place now. Computers are big too. You can buy a gigahertz machine with 2 gigabytes of RAM and a gigabyte Ethernet card for $1,200. Which, now you keep going into this thing, right? But like in 1999, one of the busiest FTP sites, CD-ROM.com, actually handled 10,000 clients simultaneously. Like, I just love that sentence because it really positions you in this like late 90s kind of mindset, right? Like FTP site, not a thing people use anymore most of the time. CD-ROMs and CD-ROM.com just like really spells out 1999 for me. I don't know. Ultimately, the point here is that like we need to be able to handle as many users as possible, especially when we're building web services. And so this is the kind of thing that like as the internet grew became more and more important. And so we had to start thinking about this. And so this is kind of where Rust's async story kind of kicks off. Even though Rust did not exist in 1999, these problems have sort of been like happening over the last 20 years to some degree. And so back in those days, we had this web server called Apache. You can still use Apache today, obviously, and I want to make a point that it is not like this today, although I think you can still technically use it like this, but I don't know why you would. This is Apache with its pre-fork behavior. And basically what happens is it would spawn, so you have this control process that would listen for a connection, somebody hits your website, and then a connection would come in and it would spawn a child process to handle that connection. And so you'd be able to do this with these resources, but this is like very, very heavy weight. This is like using like a whole process to handle things. And so then, you move into other sort of options, but like back in the day, this was like fine, but it was not like, it was too resource intensive. And so what they did was they moved to this worker model. So instead of spawning a whole process for each incoming connection, a child process would have its own thread pool with its own individual threads running inside that process. And these would be operating system, like one-to-one threads. And they would sort of hand off connections to these thread pools. And this kind of got us much farther. We were able to do more with less resources because we were no longer using this sort of like extremely heavy data structure to handle more and more traffic on the web. Okay, I'm going to stop talking about the past now. Let's actually talk a little bit about Rust, finally. 15 minutes into my presentation. So Rust was originally built by Mozilla, and the idea was that it would be enhancing Firefox, which is an HTTP client, not an HTTP server. And this does mean that we care about I/O, but the situation is very different. Like your particular instance of Firefox is not handling 10,000 requests at the same time, or 1 million requests. It's the one that's like one of those making those requests to a server. And so having efficient I/O was important because you do need to download web pages faster, but figuring out immediately how to handle massive scale was not necessarily an extreme priority because it was primarily going to be operating in this client capacity. So this is some screenshots of the old documentation for Rust. Rust originally had this module called green, and this was a green scheduling library with green threads, as I pointed out, M to N. Original Rust was like very influenced by Erlang, and actually looked much more similar to Go today than Rust actually does. Like they were much more similar way back in the day. And so Rust was like, okay, we're just going to give you these green threads because the idea is if you want to be efficient at this at all, you spin up a zillion green threads and you handle them per connection, and that's like totally fine. They also had this net library that existed. And so this was synchronous but non-blocking network I/O. And for some reason, it repeats twice. I don't know what this old bug was in the docs. If you see this module, it says the same thing 2 times. I don't know. Anyway, you were able to do very basic like TCP and UDP things in the standard library, and it was all non-blocking, and therefore also synchronous, which is weird. Like, wait a minute, I thought the whole point of like async was to be non-blocking and that synchronous would not be blocking. Turns out there's yet another thing that we didn't talk about in this space. So many things. Like, isn't this a contradiction at all? Actually, it's not. There's sort of this graph where there's only 3 out of the 4 things. So you can have these 2 dichotomies of synchronous and asynchronous I/O and blocking or non-blocking I/O. And they're actually technically different. So synchronous blocking I/O is like what the original Ruby interpreter did and what the original everything interpreter did, basically, which is you write your code in a way that looks like it blocks, and every time you call an I/O function, it blocks everything. This is very slow, but it worked really well for a while. Asynchronous and blocking doesn't really make any sense, because why are you writing your code in a way that enables you to non-block and then block on it? So I don't know any languages that actually does this, because it's like sort of nonsense. But there's actually a difference in non-blocking I/O with synchronous and asynchronous versions of this thing. And so Go and Ruby today actually offer synchronous non-blocking I/O. And what that means is when you write Go code, you're not writing it in a way that looks async. You're writing it in a way that looks like it goes through step by step by step. But inside in the runtime, it actually transparently does non-blocking I/O, and it will pause your program there. Whereas like if you look at Node.js, it's asynchronous and non-blocking. So you write all your code in an async manner, but it's also non-blocking. And so like this also, there's a ton of options in this space, and there's different reasons why different languages pick things in this trade-off. And so like we, for Rust, had to figure out like which one of these things makes any sense. Originally we picked asynchronous and non-blocking. The advantage of synchronous and blocking is like it's very straightforward, but it's like not performant at all. So that was never really going to be an option. Asynchronous and non-blocking is nice because you don't have to write your code in a different way. You just kind of write your code the way that you would normally write it, but you get some performance benefits because under the hood, the runtime does normal things. And so this is also really common in languages that start off with synchronous and blocking I/O, and they want more performance because it doesn't require your code to change in order to get faster. And so you can sort of like do it later. So I mentioned Ruby because I was familiar with Ruby beforehand, and it was kind of the same thing. Like eventually they added non-blocking I/O internally. No one's Ruby programs needed to change. Everything just kind of got faster. Asynchronous non-blocking, your code looks like it doesn't block and it doesn't block, but it's harder to write because you have to deal with asynchronicity in some fashion. So we had this blocking, blocking but asynchronous I/O in Rust, but unfortunately that wasn't good enough. See, this is what the Rust website used to look like a long time ago. And it describes Rust as a systems programming language that runs blazingly fast, prevents all crashes, and eliminates data races. But when I told you before about like green threads versus system threads, like green threads are provided by your runtime and native threads are provided by your OS, like what does it mean to be a systems programming language if you don't offer your users the ability to use system threads? Like it's like a fundamental API of the OS, but we're not going to let you use it. That seemed really like incoherent. And so we didn't think that like blocking green threads was really like the answer for Rust ultimately. And this became like one of the first big battles in Rust design. There were actually people that like threatened to fork the language over this situation. And like what ended up happening was, you'll see a couple releases later, the docs are a little fancier now, we provided this sort of native package that would give you one-to-one threading, alongside the green package that would give you the end-to-end threading. And so the idea was that you would get to choose what thing was right for your use case. You'd write some code, and it would just like, they're both threads, right? So we could just offer an API where sometimes you would use green threads if you wanted, and sometimes you would native threads if you wanted, and everything like should be totally good and dandy, right? You get all the options. Turns out that like doesn't actually really work. And so we had this whole thing, this is a bunch of text I'm not gonna read you, but basically like you write your code against this sort of runtime interface and you would pick which one. That was also not good. The battles continued. People still threatened to like actually fork Rust. Someone did, and then like 5 people faved it on GitHub, and nobody used the fork anyway. But like it was a serious problem, and like we weren't like happy with this situation. And part of the reason why is, so this is like an example of an RFC where we eventually decided to remove the runtime. So Rust is this open design process where you can submit improvements for the language, and this is RFC 230, which is the one that actually removed green threads entirely. And so what we decided was like offering both doesn't actually work. And the reason it didn't work was that in order to do the abstraction to put above both of them, you added so much bookkeeping to the green threads that they were not actually very lightweight anymore. They were just kind of a crappier version of one-to-one threads. So like they weren't actually faster in performance, and there's no reason you would pick them. And like if you gave people the ability to sort of use operating system threads and green threads, it just got way too complicated, and like it was just bad. And so with 1.0 kind of like looming, we had to decide like we're going to be freezing an interface sort of for all time. So like what do we actually do here? Because it's clear that the situation is not working, and it's clear the other situation was not working. So we decided operating system threads are part of the operating system. We're a systems language. Those things work. It's fine. Let's just do it. So Rust 1.0 shipped with a very minimal, like straightforward operating system threads. Everything is like blocking, and it's just OS threads, and you don't get anything fancy. And so that was great, and it let us get Rust 1.0 out the door, and that was awesome. This was in May of 2015, so you can see this story like started sort of in like 2011, 2012. We're up to 2015 now. We still got 4 years to go, right? 15, 19, yeah. So Rust 1.0 happened, but like still everything wasn't actually totally great. See, people really loved Rust, and that was really awesome, but that meant that they used it more. And when people start using things more, they start wanting more stuff from you. If Rust had faded into obscurity, we probably would just would have stuck with the only thread, like the thread API, and that would have been totally it, and that would have been fine. But it turns out that people wanted to build more and more stuff, and specifically, they started to really want to be able to build network services in Rust. So this is where that history with Apache comes crashing back in that like people actually didn't want to just build clients and Firefox and stuff like that. They actually wanted to be able to build network services to do stuff. And so they started building them with the existing APIs. And that led us to so Rust is supposed to be a high performance programming language, but like the IO model feels like it's out of 1999, like old school Apache, like spin up all these big heavyweight threads. And it definitely wasn't performing as well as people want it to be, even though Rust is like supposed to be a super high performance language. And like, how could we claim that like we're as fast as C while just not literally being as fast as C, because IO is like a problem. So this eventually led us to have to come up with a totally different solution as well. And so the real problem here is that native threads are a bad fit for IO. And that's because of one more dichotomy, CPU bound versus IO bound. I snuck one more definition in here. I think there might actually be 2 or 3 more. But so these are like ways to characterize different kinds of computation. So a CPU-bound computation is when your processor is doing like a lot of active work. So how fast you can do this work depends on how fast your CPU is able to crunch all those numbers and get that work done. Whereas IO-bound happens when you're doing a lot of networking, and that often means that the speed of completing the task is based on doing a lot of IO. And the problem with IO is you're often waiting on other people. So if I'm making a request to a server somewhere, it doesn't matter if I have like the fastest CPU that exists or 486. If it takes the web server 1 second to respond, I'm going to be waiting 1 second, because like it's not about my CPU. It's about the other thing in the system. And so that's like the real problem here, is that when you're doing a lot of IO, you're actually mostly just waiting around for other people. You're not making use of your CPU's resources to do that kind of stuff. You're just like waiting and doing nothing. This is why it scales, actually, because it turns out that the fastest thing to do is nothing at all. So if you have like a ton of people that are all trying to like access your website at the same time, but you're waiting on most of them, you can handle even more people because you're not actively doing work for most of your visitors. And this is why asynchronous stuff really scales up well when you're doing IO. And it turns out that parallelism is generally better for things that are CPU bound. So you kind of still want both, but like it doesn't, like, native threads and that whole model like don't really work very well in this situation. Because when you're doing a lot of waiting, if you make a thread for every single incoming connection, you're tying up all the system resources and literally doing nothing with them. So like it just doesn't work. So some other programming languages have come along that have solved these problems. I'm using Go here because it's popular and people are familiar with it, but Erlang does the same thing. Go kind of took this from Erlang, and you may recognize this from the earlier part of Rust deal. So it has asynchronous I/O, but blocking with green threads. So what happens is you write your code, and when you do an I/O call, the runtime itself will sort of sleep, and Go routines, you can map a bunch of Go routines onto a single operating system thread, and life is good. Like, you get higher performance. This is totally like a super battle-tested, well-worn way to do this kind of thing. However, previously in this presentation, you may remember this slide, and green threads have a big disadvantage, and that's when you call into C code, it's slower. This is totally fine for Go, because Go is trying to like put everything in Go, and that's also totally fine for Erlang, because like it's not that big of a deal. You're not using Erlang to crunch numbers. But Rust is supposed to be a systems programming language. So like if we did green threads, what would a systems programming language that's more expensive to call into C and operating system code like mean? Like that's also incoherent. So we couldn't really copy this model. And I want to emphasize that that's not because doing the other thing is like the wrong thing. It just turns out that when you're building different kinds of languages, you have different constraints. And so our constraints are that we had no overhead in calling into C. We designed the language itself around this kind of thing. So if we had to do it for I/O, that would be terrible. And so this is also like part of why we got rid of the green threading API that existed a long time ago too. This is like a second reason that it didn't work, but also sort of why we couldn't really return to it. But luckily, there's actually another way. There's this other web server that became popular eventually, and that's called Nginx. And Nginx did asynchronous I/O with this thing called an event loop. There was no event loop picture, so I had to draw my own. I don't know if I did a good job or not, whatever, and I flipped the arrows around. But the idea here is this thing called evented I/O, where you sort of have these events and you register handlers for each event, and then it fires off this handler whenever the event actually occurs. And this means you get really good performance, but you also don't need multiple threads because the event loop is one single thread that is handling running all these things. Most of the things are sleeping, so it's totally fine. You're not spinning up new threads for them, and it all just kind of works. So this guy named Ryan Dahl, who back in 2009 released this thing called Node.js. You may have heard of it. And it's a little hard to read in this wonderful screenshot of this terrible hand cam. This is the original like JSConf EU, so it was the first one, and it was 2009, so their AV setup wasn't that great. And you upload that to YouTube, and then you screenshot it, and you paste it into a presentation. You get this, so I'm sorry. But it says there, evented non-blocking I/O is really important. And that's kind of like the whole reason. It's the third bullet point, like what Node.js is. Server-side JavaScript, built on V8, evented non-blocking I/O. And the rest of this presentation goes into why like I/O and handling I/O is like the reason that Node existed. And Ryan cared a lot about this a lot. And so like enabling this kind of thing in a programming language was like important to him. So the issue with evented I/O is that it really requires like non-blocking APIs, because when you combine blocking code and non-blocking code together, things get awkward, but that's a whole separate talk that I cannot get into. But fundamentally, like the way this works in Node is if you have a blocking API like this top one, you call filesystem.readFileSync, and this blocks until the file is read and comes into data. But since we need to like do this asynchronously and we're registering those events so the event loop can process it, this means you have callbacks. So here's the equivalent example, asynchronous. You pass a closure into read file and you check things inside of there, and so this closure happens. This is like a minor transformation, it looks totally fine. The problem comes when you start building bigger and bigger and bigger things. You get this, callback hell. Turns out the website callbackhell.com, this is an example that they have of writing JavaScript in this style. Basically, you end up, there's also this amazing image I didn't put in the presentation, but somebody made Ryu giving a Hadouken, like this thing to the pushing everything over. I don't know if anybody plays video games here. But the point is that like when you start writing this callback stuff starts drifting right. And you can't really like do a whole lot about it. It's sort of awkward. But JavaScript people are crafty, and they came up with this thing called promises. So a promise is like an object that gives you a value that's not necessarily known when the promise is built, as the definition says. And so this lets a promise is either pending, which means that the computation isn't finished yet. It's fulfilled, meaning either it succeeded, or it was rejected, meaning the operation failed. This is fine. This lets you take code that looks like this instead. So here's an example from MDN where you create a promise, and then after a certain period of time, 250 milliseconds, you resolve it with success. And so then instead of like chaining nested callbacks, you can then say my promise.then and do another thing. And so we've removed that rightward drift because now we just chain then inline. So now we have a zillion closures vertically instead of a zillion closures indented the whole way, which is better, admittedly, but still not great for a couple of reasons, like then. The folks over at Twitter also were dealing with scale. They had originally built their stuff in Ruby on Rails, and it was not scaling in part because of I/O issues. And so they ended up rewriting everything on the JVM and being really invested in Scala. And so there was this paper called Your Serve as a Function that came out that was talking about how they built high-performance network services at Twitter. And it introduces this concept called a future, among other things. And a future is sort of like a promise, but different. It's a little tough. Basically, like, they represent the exact same ideas, but they have a different API. I'm not going to get into that at this particular moment, but we saw this happening in the Scala world, and we were like, aha, this seems awesome. And we know that like callbacks are not great because we've learned from Node, and promises are better, and futures are sort of like a different version of promise, and they seem to fit a little bit better. Scala is also statically typed. We're statically typed. Like, let's do what they're doing. And so in August of 2016, we announced zero-cost futures in Rust. And so we wanted the ability to be able to do this sort of asynchronous programming in a better way. You notice that date there, 2016. Still churning along. So here's what futures looked like at 0.1 in 2016. So you have this trait called future, and I don't know if all of you are Rust programmers or not, but basically a trait is like an interface. So this interface has two required types, an item type and an error type. And there's this function called poll, which you would call it, and it would return either the item or an error. There's also a ton of other convenience functions on here, like and then. And so you get this code at the bottom that looks very similar to that promise code, except for it says and then instead of then, because, you know, can't name everything the same way across languages. That would be too hard. But you get the same idea of like, OK, we can write these things, and this is an asynchronous computation that processes these things in this order. And so you build up these giant chains of futures. And then that chain of futures becomes a task. You submit it to the asynchronous system, and it works. And things were totally fine. As I mentioned, promises and futures are a little different. One of the other major features other than the interface aspect of promises and futures is that promises are built into the JavaScript language. And JavaScript as a language has a runtime, which means, among other things, that a promise can start executing when you make it because it's a construct the language knows, and it's able to spin stuff up in the background because JavaScript assumes that everything is asynchronous, and so nothing happens in the order that you expect. And so this is simpler in a lot of ways than the other way I'm about to describe to you, but one of the problems is that if you start executing your thing immediately, you basically need an allocation for every single thing that you've chained on because you don't know at the time that you're building the thing. Like, it's already running before you've finished like putting it together, even in some cases. And so it works, but it's not super efficient. And so futures, on the other hand, are not built into Rust the language. They're entirely a library because, again, we can't have a runtime and we can't have all this built-in stuff because we need to be as low level as C. So like, we can't afford to just do that. And that also means that unlike promises in JavaScript, you build up this chain of futures and nothing actually happens with them at all until you explicitly hand them over to an executor object and say, please run this for me in the background. And so they don't do anything until the poll method is called. And so this is a little more complicated, but it's also extremely efficient because you know how big the task is going to be when you create it. And so unlike green threads, where you make a small thing, and then when it grows too big, you have to reallocate and do all that other stuff, we can know at compile time exactly how big a task needs to be and allocate exactly the right amount of memory and never grow or shrink that stack. And you will always use a perfect, exact sized allocation, which is really cool. It also means you only have one allocation, and you can actually do this if you're willing to do like put certain limits on it. You can actually do it without dynamic allocation. You can do it statically, blah blah blah. But like this is super hyper efficient, and also because we have a compiler, and compilers are awesome, and we do everything at compile time, the futures actually compile down into the like perfect state machine that you would write by hand if you were doing the evented I/O yourself. So it becomes an extremely efficient way to do this kind of asynchronous computation, but it also is easier to write because it has this, like, it's not a bunch of nested callbacks. So here's an example of using futures 0.1. This is using a package called Tokyo, which is an executor that exists. So you have an IP address, and you create a listener, and then listener.incoming is a thing that returns a sequence of futures in a row. So on each of those, you do nothing, and then if there's an error, you print it out. So this is like just doesn't do anything, but just accepts connections. And then at the bottom here, you'll see Tokyo run. You're passing that server, like this chain of futures, into the executor, and it executes. So that's kind of like the model, the way that it worked in 2015. And so we needed to know if this is good or not, so we built a bunch of stuff on top of it. And that was really cool, but it also had some problems. So there was this thing called Futures 0.2. And one of the big problems with 0.1 and 0.2, you can see the difference here. There's this context argument, a task context. And so Futures 0.1 relied on thread local storage to sort of like deal with some bookkeeping around the future package. And that meant it relied on thread local storage, which means you couldn't use it on things like bare metal. And so that became sort of a problem. And so the intention was, what if we made this context explicit? And that would help alleviate the situation. And that was OK, but like also, we knew it wasn't perfect, and we were going to do more stuff. And so someone's like, hey, do you suggest that the ecosystem should break between 1 and 2? Or like, should we wait for 3? And Aaron, who wrote this blog post, said, you shouldn't move everything over. 2 is a good enough snapshot, but we're going to have 3 coming out in a couple of months or less. And then people were like, that seems a little bad, because like you need to try it out in order to use it. But if none of your libraries update, how are you supposed to try it out? And then if it's going to change again, why would anyone try it out in the first place? This person was smart, because as you can see, 1 year ago, we said it should be coming in a couple months. So that's sort of been a situation. Going back to JavaScript for a moment, Async-Await. So here's 3 examples of writing different code. We have the original callback kind. You make a request, you pass in a callback. Then there's promises, where it's similar, but you chain then. It looks the same in this situation, but it avoids that right-handed drift I showed you before. But finally, C# actually originally conceived of this feature. But since I was using JavaScript earlier, I decided to keep it in JavaScript. Here, you say you have an async function instead. And then you write await request. And so this actually does a sort of transformation to be able to do the same thing as the code above, but you get to write it in a way that looks like it's blocking. It goes back to like writing code in a normal fashion instead of a weird nested chain of things. So yeah, C# actually invented this first. JavaScript was like, oh, this will save us from a million promises being terrible. And life is good over there, because it lets you write code that looks like it's synchronous, even though it's not. The other way around. You write code that looks like it's not synchronous, but it actually is asynchronous. And here's the thing that's interesting that we didn't actually realize until we played with Futures 0.2 even more. But Async-Await is actually more significant to Rust than in other languages. So in C# and JavaScript, it's mostly a convenience feature, because like writing promises by hand is like a little terrible, but like it does work. But in Rust, there's no garbage collector. And what that means is that, remember that thing about how in the like promise world you create all these individual allocated things everywhere? Well, like if we did the same thing with futures, which we sort of don't, but like you're keeping track of this future accesses a thing and the next future's chain, and you're dealing with all that, it turns out that that's real hard, and Rust didn't understand that at all. And so here's an example of like a synchronous API that does read. So this is a function that takes in itself and a buffer and returns how many bytes were read or an error. And so it would look like this. You have the buffer, you have a cursor, you read in 124-bit chunks, or byte chunks, and you put stuff in the cursor. And this is like very straightforward synchronous API. So how do we turn this into futures? Like we have this great design for futures. How do we replace this synchronous version with the async version? Well, the type signature turns into this instead. And it turns out that all the code you need is actually too big to fit on this slide, so I just didn't even include it. And the reason why is because once you start chaining these futures together, the Rust compiler doesn't understand how you're using memory anymore. And so it gives you sort of like the most restrictive thing possible, which means that like your life is not good. It actually is really terrible. And the reason of this is due to that, again, like you create the thing first, and then you give it to the executor, and then it executes. And so the constraints on like checking that all the memory works the right way is different when you make that future than when you actually hand it off to be executed. And that change is a thing that the compiler just like has no idea how to handle whatsoever. And so this meant we needed to introduce more allocations, we needed to introduce more in runtime checking for a thing that like does not actually need it, but just to satisfy the compiler. And so then this in a similar way to like the green thread versus native thread abstraction, where the green threads got to be too expensive, this super hyper efficient thing didn't actually do that for any real world code. It turns out the code you had to write to use the hyper efficient thing was very inefficient. So we're now back to a place where like this is not fast and it's hard to write. So life is terrible. But Async-Await to the rescue. So with Async-Await, the compiler and the borrow checker can understand the way that these things interact with each other, and so your life becomes good again. And so here's that same API, but with Async-Await, you notice the only difference is like an async block wrapped around it and a .await there, and otherwise it looks exactly the same as the original blocking code. So we've now solved these sort of ergonomic issues through Async-Await. But there were other problems. There are always more problems. It turns out that not all futures can error. Because we had conceived of futures as being an I/O thing, we put error into the futures itself. But it turns out that it's not just an I/O thing, because once you start using futures, they infect your entire code base, and not all the things that you're doing are things that can actually fail. And so this means you add a ton of boilerplate for things that are infallible, which like seems terrible because you're making things that are easy more complicated than they need to be. And so the final design that we landed on for futures, and the one that's in the standard library soon, is called standard future. And it now has a single output type. And the signatures changed in a bunch of other interesting ways. There's this pin thing I'll get to later. And we still have our context, but now we just return the output type. And so pin is part of how Async-Await teaches the borrow checker how the code works. I'm not going to get into it because frankly, I could give you a 45-minute talk just on pin itself. It's complicated. It doesn't matter. Virtually no one, the only people who ever interact with this particular part of the API are people who are writing low-level libraries in Rust, and you as a user could not think about it, so I'm just going to ignore that it exists. Other than to say that that's what taught the borrow checker how to do these things. And then finally, if you need a future that has an error, you just compose our regular old result type as the output type. And so futures that don't have errors are fine. Futures that do have errors still work. Life is good, right? No, it turns out there's more, more problems. What syntax do you use for Async-Await? You would think this is a simple question, but it turns out that when you're designing a programming language, you have to think about edge cases. And it turns out there's a lot of edge cases that are specific to Rust that other languages didn't have to deal with. So Java and C# both do await space value. Nice and straightforward. Everything's fine. But we have this question mark thing for error handling. And you're going to use it a lot because async IO has errors. Like it's IO. It happens. So what happens if you were to copy that syntax, but you need to use the question mark for error handling? Like, does await value question mark where it's parentheses like this or like this? When you're writing this, what you want is almost always the second one, but the syntax kind of implies the first one. So it was like, should we change the precedent of the question mark operator, but only when await exists? And people were like, that seems not like a good idea. Other people were like, that's the only possible value. And so we did what most good programmers do in this situation. Oh yeah, I forgot. One more thing. So like also chaining, start chaining this with spaces. This gets nasty really quickly. And this still happens in JavaScript and sometimes in my understanding. I'm not a super big JavaScript person. But anyway, we did what everyone does on the internet. We argued and we argued and we argued and we argued. And then we argued some more. People proposed like every possible syntax for this. There was like, people were saying like, maybe we should use an upside down question mark for the one that has the different precedents. Like that was an actual, like there was people, every possible aspect of this design was like fought over. I mean like, it's not a joke. Like this is multiple threads on our discourse instance, 478 on one of those, 212 the other one. Somebody else posted the screenshot of their email inbox and was like, you can see those numbers there, like 25, 35, 100, 67, 8. Almost all these are about Async-Await, all individual threads. The Reddit had like, these are just the top 2. There were actually more threads than this, but like 168 and 133. People really like talking about syntax, as it turns out. And so the problem was that everybody hated all the options that were not their favorite, but there was no clear winner, because that's just what happens a lot of times with syntax. Everything has drawbacks, everything has positives. So at some point we decided like, hey, we can't let this incredibly important feature to Rust just be stuck down in the syntax decisions, and so we picked one. And by we, I mean other people. I didn't have to do that, thank God. So you'll notice we have this .await here. You may have noticed that it was different than the C# thing. So with no errors, you call just .await, no parentheses, because it's not a method call, it's a keyword. And with errors, you just add the question mark. Everything looks great. Some people really viscerally hate this. Other people are like, it seems weird at first, and then 15 minutes later, I forgot about it, and it's fine. I think that in the end, that's really how it's going to happen. But we ended up with a weird await syntax. It just happens. It's the best choice for Rust, I think, in the end. It was not my preferred option, but I just want to be able to use the feature. So at some point, you just got to like, yeah. But I think it's good after using it for a while. So it turns out that's actually not even the last actual issue. And this one, this is getting long, and there's too many issues, so I'm not even going to get into that one. Because this talk is long enough as it is, but like there's just always more things that happen. This one is extremely minor, so that's why I'm not talking about it. But there's other stuff we're doing with Async-Await as well that have additional like ergonomic improvements. So this is an example of a crate called runtime, and the main thing you can see here, this is a UDP example that just repeats what you say to it. But there's this runtime main annotation on the main function. So you know how it was like, oh, you have to submit your futures to an executor? Like turns out that this is a macro that does that for you. So you get code that sort of looks like the node example where you don't submit anything, but it turns out it rewrites the code so that you do. So that's kind of cool. And so we end up looking like more and more similar to a node. This is no syntax highlighting, so it gets a little messy, but it looks better in an editor. One really wild thing is that you can use Async-Await in WebAssembly with Rust. So this is an example of a program that I wrote recently in Async-Await, and it fetches some information from a database, and then there's some actual processing in here I chopped out, but what it does is it returns it as part of the response. So you notice here that this WASM entry file, it returns a promise, and that's a JavaScript promise bound to Rust. So what happens is this call to get in here, data.get, that is a call to a database that returns a promise, a JavaScript promise, because it's a JavaScript API to the database. And you need to do stuff with it. So then you turn into a future with JS future from, and this is a specific kind of future that knows how to wrap a JavaScript promise and turn it into a Rust future. Then you can call await on it. And then at the end, there's this future to promise that will take any future you have and convert it back into a JavaScript promise. So yes, this code in WASM is a JavaScript promise wrapped up in a Rust future, wrapped up in a JavaScript promise, and then returned through Rust back into WebAssembly, back into JavaScript. And this works. It's totally fine. I mean, depending on your definition of fine, I guess, but like it is a thing that if you go to my website right now, this code will execute, and it's a thing. So you can do all sorts of fun stuff with the compilers. They're great. So as I wrap up with this long and tortured story about all these different options and how we went through like every single possible thing that could have existed and figured out that all of them were terrible until our current situation, this is finally landing in Rust 1.37 or maybe Rust 1.38. Depending on that last little tiny issue that I was talking about, which is, it's fine. However, I wrote this slide, and this morning I woke up and I was going to go to the conference, and I looked at Twitter, and this is actually wrong now. It turns out that earlier this morning, Boats tweeted, like, we are actually stabilizing Async-Await for real, and that means that it will land in Rust 138 for sure, finally. All that little tiny thing doesn't matter. We figured it out. It's cool. So this Rust 1.38 is landing in, I think it's the 15th of August, so roughly in August. But like, we did it. Years later, sort of in some sense starting in the late 90s, but that's before Rust, like technically starting around like the 2010, 2011 era. 8 or 9 years later, we finally figured out how to do I/O in Rust efficiently, and it works. If you look at the latest version of the Tech Empower benchmark, which is a thing that benchmarks different website-related things, this is not the latest report, but this is like a build that happened last night or last week. Actix is one of these in Rust, and you can see that it is dominating the benchmarks. There's a whole bunch of other frameworks below there, but the next closest thing is 62% of the speed it does. And so we're able to get really, really, really high performance out of Rust network services thanks to like spending all this time sorting through all these examples and working through every possible thing led us to the like finest, fastest thing in the end that also is reasonably ergonomic to write. And so 2 lessons to take you away in my last like 30 seconds here. Turns out that a world-class I/O system implementation takes years. You can't just like make it happen. Like, surprise. Finally, different languages have different constraints. This means that you can't really argue that like Go or Erlang style is better or worse than Rust style. They have different pros and cons in all directions. And so like just because you like a thing in one language and you move to a different language does not mean that the other language did it a different way for a wrong reason. So we couldn't always just reuse things from other languages because we had different constraints about our designs. Thank you so much. That is all I have to say today.